So today we'll be presenting our LED brightness control peripheral.
So our peripheral is actually 10 different peripherals, and each peripheral is responsible for controlling one of the LEDs on the D10 board, which is why we have 10. And what each peripheral does is it's responsible for controlling the brightness level of each LED. And the reason why we decided to make it 10 peripherals is so that we could have each LED have a different brightness on the D10 board that's like independent of each other. All right, so how do we use it? Well, when you send data to the peripheral, it's gonna look at the bottom 3 bits of the data you sent, and it's going to interpret that as a binary number. So if you send the peripheral the number 0, it's gonna interpret that as 0% brightness, and the LED is gonna turn off. 1, if you send it at a 1, it would be 20% brightness. A 2 would be 40% brightness, and then so on and so forth, all the way up to 5, which would make the LED 100% brightness. And how you actually control which LED you want to change the brightness for is you use the I/O addresses of the peripheral. So for example, if you want to change the rightmost LED, you would send that data to I/O address 20, and then for the one to the left of it, LED 1, it would be 21, and then so on. And we've made sure to program gamma correction when programming our peripherals. So we've made sure that the duty cycle values are sort of on this parabola-like shape, so that when you actually go up the brightness levels, like 20, 40, 60, the brightness actually goes up linearly. Whereas if you had it on the left here, the duty cycle is just on this linear line. Then if you go up the brightnesses, the brightness level would go up in this like logarithmic curve.
Okay, so this is the application we created for our LED brightness control peripheral. We expect our 10 LEDs on the DE10 board to independently display the different brightness levels of 0%, 20%, 40, 60, 80, and 100. As shown in the video, the camera is capturing how the LEDs appear to the human naked eye. Some are dim, others are brighter, and some are completely off, etc. Our application demonstrates our peripheral functionality by displaying various patterns, but keep in mind that this is just one possible application the SCOMP user can implement. Our peripheral is designed to be user-friendly and flexible by allowing for customizable patterns depending on the user's needs. For instance, the SCOMP user can use our peripheral to visually represent the status of a system. Let's say they want a way to display the status of a game. The flashing LEDs could indicate that the game is loading, and having all LEDs be on at full brightness could indicate that the game is fully loaded and ready to start. And then having the lights be at 0% brightness could indicate that the game is currently off and not running. However, these are just some ways to utilize our peripheral for an application. The possibilities could be endless. Next, we lowered the camera exposure to better demonstrate our use of PWM, which is pulse width modulation, as we mentioned earlier in the presentation, and this is to control the LED brightness by adjusting the duty cycle. With the reduced exposure, the camera is able to capture the high-speed blinking of the LEDs, which helps create the illusion of different brightness levels. While the human eye perceives the LED as emitting a constant brightness, the camera reveals that the LED is in fact blinking rapidly. Earlier, we also mentioned that our values are gamma corrected, so this means we adjusted the duty cycle so that the changes in brightness appears more consistent to the human eye. Thank you!